Hi, everyone. All right, so with the midterm around the corner, there will be 2 review sessions this week. Tomorrow, the TAs will be holding a concept-based review session, 2050 VLSB, from 7 to 10 p.m. We know there are labs at this time, so if you're in one of those labs, feel free to attend the review session and make up the lab any other time this week. Okay. HKN will also be holding the review session, which will be more problem-oriented. And this will be on Sunday in 155 Dwinell at 4 to 7 p.m. Okay? And there will be a Piazza post about this later on. Thank you.
Hey everyone, just want to make sure nobody forgets to attend the midterm on Monday. So the midterm will be same locations as midterm 1 was, meaning most of you will be here in this room, but because there's not enough room for everybody in the class to sit in this room, some of you will be in Valley Life Science Building. Essentially, you'll be in the same place that you were in last time. For those of you who are in the Disabled Students Program and have requested extra time, your arrangements will be emailed to you probably late today. Again, there are the 2 review sessions that are coming up, one tomorrow night and one on, was it Saturday or Sunday? Sorry. Sunday, thank you. So those are posted on the class webpage now. So I won't write down the details right now, but if you want to look them up, they're on the class webpage. I believe they're on Piazza by now as well. If not, they will be. The Thursday night review session takes place during what is normally considered a lab time. If you want to attend the review instead of your lab, then for this week only, you have permission to go attend another lab. Explain to the TA where you go that you're attending an alternative lab because your lab is during the review session, and they'll let you in. Oh, and the midterm will cover everything up to the last lecture, the lecture on Monday, which means graphs, weighted graphs, Kruskal's algorithm. The material that I'm going to start covering today will not be covered on midterm 2. It'll be covered on the final. We have gotten through most of the basic data structures. There's still a few advanced data structures to come. We'll be learning about disjoint sets and splay trees later in the semester. But we're going to break away from data structures right now to talk about one of the core, or a bunch of the core algorithms. And they're all algorithms for one core problem, namely sorting things. Sorting is a pretty interesting field of study because it's one of the first places in computer science where you have a basic, fundamental, really important problem that has a huge number of algorithms for solving it. I'm sure there are more than 100 sorting algorithms in the literature, or maybe tens of thousands, depending on how much you break them down before you call them the same algorithm. In this class, we're going to learn 8 different sorting algorithms. So we're going to be pretty busy with that for a while. Sorting, again, is something really fundamental that happens all the time. If you look at a phone book, it's sorted by people's names. A computer did that, of course. If you do a Google search, the results are sorted according to what Google thinks is its importance. So it puts the searches that it thinks are most likely to be the ones you're looking for first and tries to arrange them in some priority order. We have already seen one example, and it's just one among many, of an algorithm that uses sorting for maybe a non-obvious reason. On Monday, I talked about Kruskal's algorithm. You'll recall that Kruskal's algorithm for finding a minimum spanning tree of a graph, one of the things it does is it takes all the edges in the graph and it sorts them by weight. It's not that we want sorted edges, we want something else, but sorting the edges is a means to get to what we really want, which is a minimum spanning tree. And there are many, many other algorithms where sorting is part of accomplishing some bigger goal. And of course, databases are another classic example of sorting. When you do a database query, like querying an employee database for all of the employees in manager 3 roles, usually you want to sort those the database records that you get back according to some field. Like maybe you want to sort all the managers in your company by their salary. So every database, of course, gives you the ability to sort things on a key of your choice. Sorting is one of the most fundamental problems in computer science. So today alone, we're going to cover the first 5, pardon me, because it's 2 lectures, the first 5 of those sorting algorithms. I'll handle 4 of them in the first hour. Then we're going to look at a more complicated sorting algorithm, but one that's particularly fast, called quicksort, which will pretty much take up the whole second hour. So, let's start learning sorting algorithms. We're going to start with one that you've already unwittingly implemented. It's called insertion sort. Insertion sort is very simple. It runs in big O of n squared time. That means it's not the fastest algorithm on the block, but if n, the number of items you want to sort, is small, then you're okay. If it's big, don't use this algorithm. What we're going to do is we're going to employ a list S, and the invariant that we are going to enforce is that S is always a sorted list. And so what we're going to do is we're going to take the input numbers, some unsorted list of numbers or strings, or whatever it is you want to sort, called I for input, and we're going to take items out of the input one by one, and we're going to insert them into this sorted list S. And always enforcing the invariant that when you insert a new item into S, S stays sorted. So I will write out sort of pseudocode for the algorithm here. We start with an empty list, S, and an unsorted input list, which I will call I for input, and I contains n items. We're going to take all those items out of I one by one and put them into S, keeping S sorted. So, for each item, X, in the input list, we will insert X into the list S and keeping it in sorted order. Now, this is high-level pseudocode. Obviously, I'm leaving out a lot in that last line about inserting X, but you've already done this in Homework 5. You might recall in Homework 5 you implemented a set class in which you're required to keep all the items sorted. And when you wrote the code for the insert method, you did exactly this. You figured out a way to get that item into that list so that the list was still in sorted order. So I don't have to explain how to do it because you've already done it. What about the running time of this? The running time, as I say, is n squared in the worst case, but the reason why it's n squared differs depending on the form of the list you're sorting. So I want to consider both what happens when you sort a linked list with this algorithm and what happens when you sort an array with this algorithm. So let's consider linked lists first. If we express our sorted list in the form of a linked list, which is what we did in Homework 5, then the hard part of inserting a new item is finding the right place in the list to insert the new item, and sometimes that means you have to walk through the whole list. On average, it means you have to walk through half the list. So as a general rule, it takes theta of n worst case time to find the right position to insert the item. So on average, each item is going to take linear time to insert. That's true with arrays too, but for a different reason. With arrays, it does not take theta n, worst case, time to find the place where you want to insert the new item, because you can do binary search and find that place in log n time. So there's a different issue here, which is if S is an array, well, the fastest version of insertion sort does use binary search to find the right place to insert the new item. But then, let's suppose you have to insert the new item in the middle of the list. You're going to have to shift half the items over one space in the array to make room for the new item. And that's what's going to cost n time, linear time. So I've said this before, and I'll say it again now. Linked lists and arrays both take linear time to insert something if you want to keep it in sorted order, but for different reasons. Another thing that's interesting about insertion sort is that you can create what's called an in-place sort with insertion sort on an array. So again, thinking about the case where it's an array, so what I just said is that it's an in-place sort. What that means is that if I give you an array, you can do all of the sorting in that array, like swapping around numbers in the array, without having a lot of extra workspace. You do not need a linear amount of additional working space to do the sorting in. You need a small amount of additional working space, like a few local variables, but you take very little extra memory to do the sort because you're sorting right within the array. So you're using, although the array itself takes up a linear amount of memory, the amount of extra memory that you have to use to do the sort is only a constant, or maybe in some algorithms that we'll see log n in the worst case. So here's how we do an in-place insertion sort. Suppose somebody gives me this array to sort. So this is the input array, I. It's unsorted. Now, the code I gave you says we take items out of there one at a time and we put them into a sorted array S. But I want to do that in place, which means I can't create a whole extra array. I don't want to allocate that much extra memory. I want to do all the sorting right in this array. How do I do that? Well, what I'm going to do is I'm going to say that I'm going to divide this array into two different pieces. On the left, I'm going to keep the sorted numbers. On the right, I'm going to keep the unsorted numbers. Initially, all the numbers are unsorted and nothing is sorted, but I'm going to take the first item, the 7, and I'm going to say, okay, now that item is sorted. So we go to a state where we now think of this array as being divided into two separate pieces, with the first part being the sorted part and the second part being the unsorted part. So there's an imaginary line here between them, which is really a loop index, but you pretend that this is two separate arrays, even though it's only one. And now I'm going to take the next number in the unsorted array, the 3, and I'm going to insert it into S, the sorted array. So when I insert 3 into S, that means I have to put it in its correct order before the 7. So now I have the sorted part of the array is 2 items, because I've put the 3 in its proper place. The unsorted part of the array hasn't changed at all. except that it's one item smaller. Now I'm going to do it again. I'm going to take the next item, the 9, and I'm going to insert it into the sorted part of the array. And I have to insert it in its proper place. So now I've got the sorted part of the array. I've just inserted the 9 in its proper place. And I still have one item left that has not been added to the sort yet. And then finally, I will insert that 5 into the rest of the array. And now the whole array is sorted. Nothing is left unsorted. And I didn't have to use any extra memory except for a few local variables. One thing that's really interesting about this is that there are certain special circumstances where if your input array is almost sorted, meaning it's close to being sorted but maybe a few numbers are out of place, this is actually much faster than n squared. Insertion sort is really fast at sorting almost sorted arrays. The running time is proportional to the number of inversions. An inversion is a pair of numbers that are in the wrong order in the input array. And since there are order n squared different ways to pair up all the numbers, there could be n squared inversions, but if there's only a linear number of inversions, this will run in linear time. What else to say about this? Well, in the worst case, each of these insertion steps takes linear time. If you have an almost sorted array and you want this to run fast, your insertion routine should go from right to left. So if I want to insert a number into this array, I should start at the end and work backwards when I'm looking for the right place to insert the new item. That ensures that the running time will be just the number of inversions. Are there any questions about how insertion sort works? Yes? Mm-hmm. So if this is your input list I, then every pair that are in the wrong order is one inversion. So 17 and 9 are one inversion. 9 and 5 are one inversion. 17 and 5 are one inversion. So in this example, we have 3 inversions, and the total cost of insertion sort is going to be proportional to 3 plus a small constant. And so you can see that if you have a list where it's initially completely reverse sorted, all the numbers are in backward order, then every pair of numbers will be an inversion, and that's when it takes n squared time for insertion sort to run. Yes?
Does insertion sort run quickly for the sorted list if you're sorting a list?
Say that again?
Does insertion sort run quickly on nearly sorted lists?
Okay. So yes, you can get insertion sort to run just as quickly, proportional to the number of inversions, on linked lists. To do that, you either have to use a D-list, or you have to store the numbers in an S-list in backward order. And the reason why is because for insertion sort to be fast on almost sorted lists, you always have to start the search from the end of the sorted list and work backward. But if you do it right, yeah, you'll get fast performance. Mm-hmm. Uh-huh. You mean this input list here? 3 and 9 is not an inversion. So those two are already in the correct order, so that doesn't count as an inversion. The inversions in this list are, well, 7 and 3 are in the wrong order. 7 and 5 are in the wrong order. 9 and 5 are in the wrong order. I think that's it. So yeah. So again, the running time is proportional to the number of inversions plus n, because if there are no inversions, you still have to walk through the array. One other thing I want to mention briefly about this sorting method is that you could imagine that S is not an array, but rather S is a balanced search tree, like a 2, 3, 4 tree. And if you did that, then the running time would actually be faster. The running time would now be in big O of n log n, because you can insert anything into a 2, 3, 4 tree in log n time. So by using a fancy data structure, suddenly you have a much faster version of insertion sort. That n log n is a big improvement over n squared. Having said that, this is still kind of a complicated way to get an n log n sorting algorithm, and we'll see that there are a lot of simpler ways to get n log n sorting algorithms. So we're going to overlook this one in favor of some other faster or simpler ones. I'm going to move on to sort number 2 now. Selection sort is equally simple as insertion sort, and it's an equally obvious idea. It also runs in quadratic time. Though there actually is a difference. Insertion sort runs in quadratic worst case time. Selection sort runs in quadratic time. Worst case, best case, it's always slow. Nevertheless, it's worth knowing for a variety of reasons. We are going to maintain, again, the same invariant that we have a sorted list S, but we're going to structure things differently. Instead of keeping the list S sorted by looking through S and finding the right place to insert a new item, instead, here's what we're going to do. We're going to walk through I, the unsorted list, and find the smallest item. Once we find the smallest item, we'll just pick it out and we'll put it at the end of S. We don't have to search for S for the right position to put the new item, because the right position to put the new item is always at the end of S, because we always pick the smallest item out of I. So we will start exactly as we did with insertion sort. You have an unsorted list S and a sorted list I of n items. And now what we're going to do is just loop n times. We're going to let x be the item that's still remaining in the unsorted list that has the smallest key. We're going to remove that item from I and append it to the end of S. That's the algorithm. So, how long does this take? Well, the slow step is the one where we go through I and we find the item with the smallest key. Finding the item with the smallest key in an unsorted list, you have to look through the whole list. You have to check every item because you don't know which one's going to be smallest. So that takes linear time. Every time we do this line here, that line takes linear time, and if we just keep it as an unsorted list, there's no way around that. Doesn't matter whether we're maintaining this as a linked list or an array. Either way, finding the smallest item is going to take linear time. So, overall, the whole algorithm takes theta n squared time to do selection sort, even in the best case. which makes it sound like it's not worth studying, but actually it is worth studying because we're going to find some ways to use it or to modify it that make it faster. But in its general form, it's not very good. But it is in place, so let me show you how you can do an in-place selection sort. I'm going to take the same array we had before, 7, 3, 9, 5. And again, initially we're treating this as an insorted array. What we're going to do now is we're going to go through that array and we're going to pick out the smallest number in the array, which is a 3. And once we've found the smallest number, we're going to swap it with whatever item is in the first position. So this is just a swap. You swap 3 with 7. 9 and 5 were unaffected by that. And now the first item, this 3, that's going to be the sorted portion of my array. And that leaves me with 3 items that I have not yet sorted. So again, I go through those 3 items, and I pick out which one is the smallest. 5. Once I found the smallest item, I swap it with the first item in I. So I move it to the beginning of I. So we've got the 3 there and the 5 there. The 5 was swapped with the 7. The 9 was not even touched. And now we can move this barrier again, and we can say that the first 2 items have been sorted, and there are 2 items left that have not been sorted. Pick out the smallest item that has not yet been sorted, that's the 7. Swap it with the first item in I. And with selection sort, when you get to the point where you've sorted all the items but one, you've really sorted all the items. You can skip the last iteration of the loop, because all you're ever going to do is swap the 9 with itself. So this is essentially an imaginary step here where I don't actually have to do anything. I just have to imagine that now the whole array is S and I is gone. Any questions about selection sort? All right, so, question? Okay. Let's ask what happens if our unsorted list is not just an unsorted array, but a faster data structure like a binary heap. Then you get a different sorting algorithm. It's still a selection sort, but we don't call it selection sort anymore. We call it heap sort. So, again, heap sort is a selection sort. It's a kind of selection sort in which I stops being an unsorted array and starts being a heap. So here's our algorithm. We're going to start with the usual empty list S and I. So this is the same line that I started the last 2 algorithms with, so I'm not going to rewrite it in full. But we're going to take all of the items that were given, and we're going to call them a heap. Except we have not yet enforced the heap order property. So really, if you're using an array-based heap sort and your input is an array, this step doesn't actually do anything. You've just got an array, and now you're calling that array a heap. But it doesn't yet obey the heap order property, so we need to make it obey the heap order property. And we have an algorithm for doing that, which is in the lecture notes for the lecture I gave on binary heaps. So you might recall that there is an algorithm that in linear time will take an unordered array and convert it into a heap. If you don't recall that, well, then just imagine going through the items one by one and inserting them into a heap, which you could do that in log n time per item. That would be n log n time total. There's actually, again, a faster way to do it that takes linear time, but for the purposes of understanding the asymptotic running time of heap sort, it doesn't matter which one you use. Once we've got our items in the form of a heap, then we're just going to treat it like an event simulation and take items off the heap one by one, and because it's a heap, they're going to come off in the correct order. So I just need a loop that iterates n times. And each iteration is a remove min operation. And you take the thing that you've just removed from the heap, the minimum key, and you append it to the end of S, just like in a selection sort. And that's the algorithm. So again, some reminders about running time. This bottom-up heap step runs in big O of n time. And the remove min operation, each time we run it, takes big O of log n time. And how many times do we run it? We run it n times, because this loop here runs n times. So multiply n by big O of log n, and that's the dominant running time of heap sort, is n log n. Now, one thing that's kind of psychotic about heap sort is you can actually do it in place. So let's take a look at that. There are actually several ways you can do heap sort in place. I'll tell you one today, and you'll see another one in a movie around the end of the semester. But the one I'm going to tell you about today is we're going to maintain the heap backward at the end of the array. And the reason we're going to do that is because remember that we're trying to keep two different lists in one array. The sorted list S on the left, the unsorted list I on the right, which is going to be a heap now. So I want to make sure that as I take items out of the heap and the sorted list grows from the left, that the heap is shrinking towards the right at the same time. And the way to make sure that the heap is shrinking towards the right end of the array is to store it at the right end of the array in backward order. So we take the level numbering and we reverse it. And that makes things work out so that you always can fit everything into the array. So let's look at that array we were sorting again. Make it a little smaller here. 7, 3, 9, 5. All right, the first thing I'm going to do is I'm going to interpret this as a heap, or I'm going to interpret it in terms of level numbering. And again, I am maintaining the heap backward at the end of the array, which means I start from the right and I read towards the left. And I'm going to read the first number to be the root, and then the left child of the root, and then the right child of the root, and then the left child of the left child. And so doing reverse level numbering, 5 is the root, 9 is its left child, 3 is its right child, and 7 is the left child of the 9. Again, you get this just by starting at the right, reading towards the left, start with the root, and just fill the numbers into the tree level by level. This is not a heap yet. We need to run the algorithm called bottom-up heap that will convert this into a heap by a sequence of swaps. And so when you do bottom-up heap, it goes through the internal nodes of the tree in reverse order and bubbles them down. So it starts with the 9, bubbles the 9 down. Then it visits the root, the 5, and bubbles the 5 down. So after you do that, you're going to get a tree that looks like this. Two swaps took place. The 9 got traded with its child, the 7. The 5 got swapped with its child, the 3. And now this satisfies the heap order property. This is actually a real heap now. As it happens, we're really doing these operations in the array. It's easier to understand them when you draw them as a tree, but your computer code is going to be working on this array, swapping items in the array. And now, with reverse level numbering, your tree looks like that in the array. Now that we have a heap, we can start removing items from the heap one by one. So we do remove min. And when you do remove min to this heap, you remove the 3 from the root. Now the root is gone. We need to replace the root with something, so we take the 9, we move the 9 up to the root, and we bubble it down. And after we've done that, it's going to look like this. That's our new heap after remove min. And when we look at the array, we're going to see that in reverse level numbering, the heap looks like that, 5, 7, 9. Also, because the heap only has 3 items now, there's an extra space there where we can take the minimum key we just removed from the heap. Now we have a place to store it. So that 3 we removed, it goes here in the unsorted part of the list. In the sorted part of the list. And the remainder of the heap is still considered to be unsorted, but it's not completely unsorted because it still satisfies the heap order property. And so we do another remove min. And after removing the 5, now our heap looks like this. In the array, that means using reverse level numbering, the 7 goes there, and the 9 goes there. And that's what the heap looks like. The rest of the array, again, is going to be for the items that we've removed so far. So the 3, we don't touch that. The 5 that we just removed from the heap goes into the empty space that just got freed up. So now we have 2 sorted items. We do another remove min. The 7 gets removed. Now the heap is just a 9 at the top. So here's our array. There's our heap. It's just a 9 now. The 3 and the 5, we didn't even have to look at them. The 7 that we just removed from the heap goes into the array. Finally, we're going to remove the 9 and put it at the end of the array. And now the entire array is sorted. So that's heap sort. Any questions about that? Mm-hmm. It's up to you, actually. The question is, do you really do remove min on the 9? Just like in selection sort, you can actually skip the last iteration of the loop because it will always be the case that when you get down to one unsorted item remaining, it will already be in the correct position and you're finished. You don't have to do the last loop iteration. It does no harm if you do, but it just wastes time. Question over there. Why must you what? I don't have... There's a page of the Goodrich and Thomasia book that has a figure that illustrates that really well. I don't have time to reconstruct it right now, but I really recommend... the page number is listed in the lecture notes for the binary heap. I really recommend looking at that figure and studying it just till you understand it, because it's a really beautiful, simple, pictorial idea, but I don't remember how to reproduce it off the top of my head, so please go look at that page. Shifting the unordered part. So I'm following the standard rules for binary heaps that I taught in the lecture on binary heap. And those rules are not simple, so I've given the time now, my best recommendation is go read the lecture notes. But the short version is just remember that we were always taking the last item in the level numbering and getting rid of it by moving it up to the root and then bubbling it down. And that means that you will always be left with an empty space at what was the last item in the level numbering. And since we're storing the heap in reverse level numbering, that's always going to free up a space where we can store the next sorted item. So one thing about heap sort, by the way, is that it is excellent for arrays. Because it runs in n log n time, it's really fast, and it's an in-place sort, so it's really memory efficient too. But it's really awkward for linked lists. It really is not the sort of choice for linked lists, because how do you sort linked lists with heap sort? Honestly, the most elegant way to do it is construct a new array. The array will have references to all the list nodes. Sort the array, and when you're done sorting the array, like this, then reassemble the list nodes into their new correct order. That's how you do heap sort on a linked list. So it's not memory efficient, and there are other algorithms that are more suited to linked lists than heap sort. But heap sort's great for arrays. I will go on to algorithm number 4 now, which actually is kind of the opposite in that it's very well suited to linked lists and not very well suited to arrays. It's called merge sort. Merge sort is based on the observation that it's possible to merge two sorted lists together into one sorted list in linear time. In fact, how do we do that? One way to think about it is as a selection sort on two queues. So let's just suppose that we have two sorted lists and we express them as queues. So I'll call them Q1 and Q2. Also, I'm going to create an empty queue called just Q, which is going to be the destination where I put all the sorted items. Now, as long as the input queues are not empty, what I'm going to do is I'm going to look at the item at the front of Q1, I'm going to look at the item at the front of Q2, I'm going to compare them Whichever one is smaller, I'll take it out and put it into the output list queue. So let's look at the item at the front of Q1. Let's look at the item at the front of Q2. And whichever one is smaller, compare them. Whichever one is smaller, move it from where it is now to Q. Eventually, one of the two queues is going to be empty, and then the other one's not empty. You just take all the stuff that's in the non-empty queue, and you concatenate it to the end of the output queue. You have sort of seen this before. Again, this is something you've done for Homework 5. You'll recall that in Homework 5, you implemented a union operation where you compute the union of two sets, and we asked you to do it in linear time. So if you did it right, you essentially did this, walking through the two sets, checking which one has a smaller item at the front of the queue, and moving that to the output queue. There's just one difference. When you were computing the union of sets, if there was a duplicate item, meaning if there was an item in both Q1 and Q2, you would only have one copy of that in the output. Here, we're not doing sets, we're doing sorting. So if you have multiple copies of the same key, you copy all of them to the output. You don't get rid of duplicates. So one way to look at this merging routine, by the way, is this is a selection sort. So we're just doing selection. We're finding the smallest item, and we're moving it to the end of the output list. But selection is really fast in this case because we're sorting two sorted lists rather than sorting a big unstructured mess of numbers. And so now selection is fast enough to actually be worth using, because you can merge two queues in linear time. Once you have the ability to merge two queues in linear time, or two sorted lists in linear time, then we can build a sorting algorithm out of that with using this as a subroutine. Merge sort is what's called a divide and conquer algorithm. It is recursive. What merge sort does is it divides your unsorted list of numbers into two separate unsorted lists of numbers in no particularly interesting way, just divides it into two sets. It recursively sorts each of those two sets separately, and then it merges them together into one sorted list. And that's the conquer part, is when you remerge the two lists that you divided. So here's the actual algorithm. We start with an unsorted list called I for input of n items that we want to sort. We're going to break I into two halves. So we're just going to take the first half of the items and call them I1. We'll take the second half of the items and call them I2. So each list has about n over 2 numbers. If you want to be precise, the first list will have n over 2 ceiling numbers, and the second list will have n over 2 floor numbers to sort. So if n is odd, well, obviously you can't divide it into 2 exactly equal piles, but you get as close as possible. Then we're going to sort I1 recursively with merge sort. Let's just assume that merge sort works. So after you sort it recursively, you get back a sorted list of the same items, which we will call S1. And then we sort I2 recursively, yielding a sorted list that we will call S2. And finally, we will use that merge routine that I wrote above to merge S1 and S2 together into one sorted list. And I'll call that sorted list S. That's the output. And that's merge sort. So let me show you a pictorial way of imagining what this algorithm is doing. Let's suppose that I have a list of 8 items. Let's not worry yet about what particular numbers I'm sorting. We're going to take those 8 items and break them up into 2 groups of 4 and do a recursive call on each of those 2 groups of 4. So there's a group of 4 here. And there's another group of 4 here. And we will recursively call merge sort on those. And what do? Well, they take those 4 items and break them up into 2 lists of 2. And recursively call merge sort on those. Now we've got lists of length 2. We call merge sort recursively again, breaking this all down to lists of length 1. In merge sort, the recursion bottoms out when you get to a list of length 1. So a list of length 1 is already sorted. You can stop there. What I've just drawn here on the board, this is a tree that shows you the structure of a sequence of recursive merge sort calls. So it's a little bit like a game tree. This is not a data structure. You do not actually create a tree data structure. Just like when I was drawing the pictures for game tree search, this just tells you what all the recursive merge sort calls are. So when you get down to the bottom, let's suppose that the numbers that you wanted to sort were 7, 3, 9, 5, 4, 8, 0, 1. What happens? Well, after we get down to the bottom of the recursion here, we go up a level and we merge this list 7 with this list 3. Using that selection sort that I showed you. And so now we have a merged list 3 and 7. The same thing happens here. I'm going to merge these 2 lists, and that'll give me a sorted list 5, 9. I backtrack up 1 level, and now I can merge the list 3, 7 with the list 5, 9. So I start walking through both lists. Which is smaller, 3 or 5? 3. Which is smaller, 5 or 7? 5. Which is smaller, 7 or 9? 7. And then the 9 goes at the end. And likewise on the right-hand side, merge 4 and 8, you get 4, 8. Merge 0 and 1, you get 0, 1. Merge those 2 lists, you get 0, 1, 4, 8. Finally, at the very top of the recursion, the very first merge sort call merges the 2 big lists into 0, 1, 3, 4, 5, 7, 8, 9. And that is how merge sort is done. What about the running time of this? Well, let's count how many levels there are in this recursion tree. It turns out that if you have n items you want to sort, then you're going to get 1 plus, well, you take the base 2 logarithm of n, and you take the ceiling of that, and that tells you how many levels there are in this tree. So that's a really useful piece of information, because at every level of the tree, we're doing the same amount of work. The time it takes to merge two lists is linear time in the sizes of those lists. As you go down the tree, you get more and more lists, but the lists are smaller and smaller. The total amount of work at each level of the tree is always linear work per level. And that is why merge sort runs in order n log n time. Any questions about merge sort? If the length was an odd number, then things still work. So if you have seven items, then the recursion will give you 4 items here and 3 items here. And then 2 and 2, and 2 and 1. And then these ones will bottom out at a different level. And that lonely one on the far right will stop one level early. So, the leaves are not always at the same level. They can differ by 1 level, but it still works out in the end. And that is why when I wrote the number of levels, the reason I wrote a ceiling here is because if n is not a power of 2, that's going to be some fraction. Mm-hmm. No matter what list you have, it's always, yeah, it is. Okay. So, good point. It is theta n log n, both in the best case and the worst case. Uh-huh. I'm sorry, what was the last thing you said? No matter how well sorted the data is, yeah, if you have data that's already sorted or partly sorted, this does not take advantage of that in any way. So, yeah, you're right. One thing that differentiates merge sort from the other algorithms we've looked at is it's really not an in-place algorithm. People have tried to figure out versions of merge sort that you could run in place, and they just have turned out to be terribly, terribly complicated. No researcher has ever figured out one that would be simple enough, a simple enough in-place merge sort that you'd actually want to use it. So, merge sort. If you are sorting an array with merge sort, you usually use an extra array that is also of linear length to temporarily hold the result of a merge. So that's kind of a disadvantage of heap sort, is if you want to sort arrays, then the best way to do it in practice is to use twice as much memory as what heap sort would need. Any questions about that? All right, on to sort number 5, which in some ways is the big daddy of sorts. It's called quicksort. Like merge sort, it is a recursive divide and conquer algorithm. The difference is that heap sort does all the work up front. At the end. I'm getting mixed up. Merge sort does all the work at the end. So in merge sort, when you're dividing a list into 2 lists, that's no work at all. When you're merging those lists back together, you're doing a selection sort. That's where all the work occurs, is at the end, at the conquer part of divide and conquer. Quicksort is the opposite of that. Quicksort does all the work in the beginning, in the divide stage, and then the conquer stage, the merging stage at the end, is easy. Quicksort happens to be the fastest comparison-based sort for arrays. And I mean fastest in practice, and I am including the constants hidden in the big O notation. So this is just something that's been observed to run really, really fast in practice. And yet, I'm going to sound like I'm contradicting myself here, but its worst case running time is n squared. However, if it's implemented correctly, it virtually always runs in big O of n log n time. So for all practical purposes, it is an n log n time algorithm. And I'll show you later in the semester how to use probability theory to analyze it and show that it runs in expected n log n time. But there's always a tiny probability that it might run in n squared time, probably much smaller than the probability of your being killed by a meteor in the next hour, so probably not a big thing to worry about. I'll mention that usually quicksort is significantly faster than merge sort for sorting arrays because it has nice tight inner loops that give you a really small constant in the big O. But if you're sorting linked lists, quicksort doesn't necessarily have the same advantage. Sometimes merge sort runs faster than quicksort. For sorting linked lists, it depends how you implement them. All right, so the way quicksort works is we're given some unsorted input. We're going to choose some element, some item in it, to be what's called the pivot element. And the pivot element is going to be used to partition the input into 2 separate lists, a list of items that are less than the pivot and a list of items that are greater than the pivot. So we start with an unsorted list I of n input items. We will choose a special item that we will call a pivot item, and I will call it V from that list. I'll talk about how to choose the pivot later. For now, just choose an arbitrary number out of the list. And then we're going to use that pivot to partition the input into 2 lists. I'm going to call those lists I1 and I2. And they're going to be unsorted lists. We haven't sorted them yet. But they will differ in one important aspect, which is I1 will contain all the keys that are smaller than the pivot's key. And I2, the second list, will contain all the keys that are greater than the pivot's key. So what about keys that are equal to the pivot? Well, those can go into either list. We'll talk more about that later. And in fact, how we do this is going to be a crucial decision, but it's going to be different for linked lists than for arrays. So that's why we're going to put off talking about that till later. However, whatever you do with items that have the same key as the pivot itself has to be treated specially. The pivot does not go into either list. And that's very important. So that is how we partition items. Now that we've partitioned them, what next? We sort these two lists recursively. So now we sort the first list, all the keys that are less than the pivot, by calling quicksort. And we'll assume that quicksort works correctly and gives us a sorted list, which we'll call S1. And we'll do the same thing for I2. We will sort I2 with quicksort, yielding a sorted list that we will call S2. Once we've got those sorted lists, then it's easy. You just glue them together. Either all the items in S1 are sorted and they come before all the items in S2. So you just glue them together with a pivot in the middle. The recursion will bottom out when we reach a list of size 0 or 1. That's where we stop. Any list of size 0 or 1 is sorted, so we just return it back up the recursion. I'm going to give some examples of this, but before I do, are there any clarification questions about this algorithm? Okay, so well, let's see what this algorithm does. So I'm going to give you a couple of examples. I want to show you what can go right, and then I want to show you what can go wrong. So let's start with what can go right. Here is an array of 7 items, 4, 7, 1, 5, 9, 3, 0. For now, I'm going to use the rule that the pivot is always just going to be the first item in the array. So when I start, I'll make 4 my pivot. So what I do is I walk through the array from left to right, skipping the pivot, and each item goes either into the list of items that are less than the pivot or the list of items that are greater than the pivot. So start with 4 as the pivot, then there's a 7. The 7 is going to go into the list of items to the right, because it's bigger than the pivot 4. Then there's a 1. 1 is less than the pivot 4, so I'm going to put that in a different list of items that are less than the pivot. Then there's a 5. 5 is greater than the pivot. Then there's a 9. 9 is greater than the pivot. Then there's a 3, which is less than the pivot. Then there's a 0, which is less than the pivot. So now that gives me those lists I told you about, I1, keys that are less than the pivot, I2, keys that are greater than the pivot. I'm going to sort those two recursively. After they're sorted, I'm going to glue them together with the pivot in the middle. So here's the pivot, V. So now I call quicksort recursively on those two arrays. I have an array 1, 3, 0. I pick the first key to be the pivot, so 1 is the pivot, and then I partition the rest of the array into keys that are less than the pivot, like 0, and keys that are greater than the pivot, like 3, and I have the pivot in the middle. So once again, here's the pivot, here's the unsorted array I1 recursively, here's the unsorted array I2 recursively. But when you have an array of length 1, it's sorted, so we're done with the recursion on that side. On the other side, we'll do the same thing. 7, 5, 9, we say 7 is the pivot, we make a list of keys less than the pivot, keys greater than the pivot, and we put the pivot in the middle between them. So there's an unsorted array I1 and our unsorted array I2. Again, those only have one key, so they're sorted. So basically now we're done. We just need to take these numbers that were created as we went along and glue them together into big lists. And that's sorted. So in this example, things worked out really well. We got a recursion tree for quicksort that's really nicely balanced. And so this was pretty fast. This was as fast as merge sort. Let's look now at what can go wrong. One of the things that can really, really go wrong is, I told you that this rule that we use is that we're going to just pick the first key to be the pivot. Well, it turns out that's a really bad idea if your list is already sorted. So I want to sort this list. It's already sorted, but I don't know that. Someone just gave me a pile of numbers. I don't know that they're sorted. I just throw quicksort at it, make sure that they're sorted. So here what happens, well, we pick the first item to be the pivot, and that's a 0. So now we take all the keys that are less than 0 and put them on the left-hand side, take all the keys that are greater than 0, put them on the right-hand side. Well, all the keys that are less than 0, there aren't any, so we get a subarray of length 0 on the left. All the keys that are greater than 0, well, that's everything except the pivot. And we put the 0 in the middle. So that's our unsorted array I1 on the left is empty. Our unsorted array I2 on the right is still pretty full, and the pivot is between them. Now we recurse on the right-hand side. We pick the leftmost key to be the pivot, and that's a 1. So now you'll notice we'll get the same kind of disaster all over again. And you can see we're getting a pretty unbalanced split here. When you get an unbalanced split, that's just not a good thing, and I think you can see where this is going. It's going very, very slowly to being a sorted array, but not nearly as quickly as we would like it to. So this is kind of a mess. It's, you may notice, turning into a quadratic times sorting algorithm. And there we're finally done, but it took quadratic time to do it. So this sucks. It's a disaster to use the pivoting rule that we always choose the first item to be the pivot if the array is already sorted. This won't do it all. We need a better pivoting rule. So you see, we span the range from, you could get a perfectly balanced tree if you're really lucky, and the whole thing will run in n log n time, just like merge sort because you're going to have about log n levels of the recursion tree and at most order n time per level. And if things don't work out well, then you can get theta n squared worst case time. So let me write down what I just said. When input is already sorted, choosing the pivot to be the first item is just a disastrous policy. Any questions about how quicksort works before I talk about how to choose a better pivot? The first one is n log n for the same reason merge sort was, that if you happen to get perfect splits, then you have big O of log n levels of this recursion tree, and at every level of the recursion tree, it is order n time per level. And most of that order n time is doing the partitioning. The partitioning step takes linear time. Other questions? So I want to talk about how to choose a better pivot. The answer might surprise you. Researchers have tried lots of things, and the time-tested thing that works really well and reasonably quickly is to pick a pivot randomly. Flip a coin. It's actually really surprising how well this works and how it tends to work better than anything non-random that anybody has thought of. For instance, when I talked about this tree being order n log n time, that is actually the expected running time, not the worst case time, which is n squared, but the expected running time in a formal probabilistic sense. You can prove using probability theory that if you choose a random pivot, that quicksort will run in expected n log n time. And I will actually show you a proof of that later in the semester. But the important thing to understand for now is that on average, and I'm using that term loosely, I'm not being mathematically precise here, but on average, you can expect a 1/4, 3/4 split. Now, you cannot expect to get a perfect 50-50 split like you can get in merge sort. You do not quite that well. On average, we're going to get 1/4 of the items on one side of the partition, 3/4 of the items on the other side. Half the time we will actually do worse than that, meaning even more unbalanced. Half the time we'll do better than that, meaning more balanced. But even though it's unbalanced compared to merge sort, and that means you might get a deeper recursion tree, quicksort has some advantages that still make it faster for sorting arrays. If you want to know why you get a 1/4, 3/4 split on average, I'll just mention that Goodrich and Tomasia have an explanation of that in section 11.2.1 of their book, if you have the 5th edition. If you have a different edition, you'll have to figure out what section that's in. But they show that the average running time in a probabilistic sense is in n log n. And again, I will talk about that later in the semester. One other thing that's worth mentioning is that picking a random pivot works pretty well in practice. When you have still a relatively large array, like if you've got at least 50 keys or so to sort in the recursion, the level of the recursion that you're at, researchers have found that it can be even better to pick what's called a median of 3 strategy. That means instead of picking one random key to be your pivot, you pick 3 random keys. You look at which of those 3 random keys is in the middle, the median, and you use that as your pivot. And again, you can analyze that with probability theory and show that that will tend to give you better balanced splits. But it takes a little longer to choose the pivot, so it's only worth doing if you're sorting at least 50 numbers or so. All right, I left a lot of details out of how to do quicksort, especially how do you deal with keys that are the same as the pivot. And we're going to see that you want to do that differently for linked lists than for arrays, because there's tricky things you have to do to make in-place array quicksort work. So let's start with linked lists, because that's easier to understand. So quicksort on linked lists. What do you do with keys that are equal to the pivot? Well, we could just put them all into one of the lists, like I1. So let's see what happens if we do that. Suppose we put all items with the same key as V into list I1. Will quicksort work if I do that? Yes, yes, it will. Will it work fast? Unfortunately, no. And here's why. One special case that you should always worry about is, does my sorting algorithm run fast if all the keys are the same? So here's an array full of 5s. Well, it's already sorted, but we don't know that. We don't know it's all 5s. We're just blindly running our sorting algorithm on that list. And maybe it's not all 5s, maybe it's just mostly 5s. But what happens if I use this rule that says all keys equal to the pivot go into I1? Well, then what's going to happen is all these 5s are going to go into I1. And the pivot goes out separately, and thank goodness for that, because otherwise this would run forever. And I2 will just be an empty list. And so now you've got a recursive quicksort call on those 5s. And again, it doesn't matter which one is the pivot. You're going to do the same thing over again. And you can see where we're going here. We're going for n-squared performance again. So this policy is no good. Putting all the keys equal to the pivot in I1 means n-squared running time when all the keys are the same. Not acceptable. We need to do something else. All right, so here's the better solution, but only really works for linked lists. This is not going to work for in-place array quicksort. For linked lists, though, we can just partition I into 3 linked lists. And let's call them I1, items that are less than the key, I2, items that are greater than the key, and IV is going to be items equal to the pivot key. And what the hell, let's throw in the actual pivot too. So IV will contain the pivot, V, and all the items with the same key as the pivot. So now what will happen if I try to sort this array of all 5s? We'll get 3 lists. I1 will be empty, because there are no keys less than 5. I2 will be empty, because there are no keys greater than 5. IV will contain all the 5s. And since they all have the same key, we do not sort IV recursively. It's already sorted. So now we're going to have a quicksort that runs in linear time if all the keys are equal to each other. And that's great. Let me just show you a slightly more sophisticated example, because we also care about having fast performance when almost all the keys are the same, but not all of them are the same. So here's an array that's just mostly 5s. We will still separate out the keys that are less than 5 and the keys that are greater than 5, and we will sort those recursively. But all the keys that are equal to 5, they get pulled out into a separate linked list. They're already in sorted order, so we do not have to recursively call quicksort on IV. We're done with that, and now we can do the rest of the sorting really fast because there's not much sorting left to do. And then, of course, when we're done, we'll concatenate the recursively sorted list S1, the doesn't need to be sorted list IV, and the recursively sorted list S2 to get the output. And so with this little change, we add one extra list called IV. We've made a quicksort that was really, really slow when you have lots of keys that are equal to a sort that's really, really fast when you have lots of keys that are equal. Any questions about that? Mm-hmm.
What about this is specific to linked lists as opposed to arrays?
Well, if you're doing arrays and you're doing in-place arrays, meaning that you cannot have a whole bunch of arrays, but you've just got the one that you were given as input, then it is not easy to partition into 3 separate lists that are all in the right position in the array. If you try writing the code for that, you'll find it's a messy pain. You can do it if you think hard enough, but then you're also going to find out that it's slow, that the big O factor is much bigger than it is for the code that just partitions into 2 lists. And therefore, you lose the advantage of quicksort, which is it's usually the fastest sort. The only real way to understand that is to actually try to write the code and see what happens. But trust me when I say that partitioning into 3 arrays like this, 3 different sets, in place in an array, is complicated and therefore slow. Other questions? I'm going to talk about how we do quicksort on arrays. And one thing you'll see about this is that when you're just partitioning into 2 lists, you can write really tight code that does this very fast. And that's part of the secret of why quicksort just happens to be the fastest comparison-based sort in practice. So in-place quicksort is really fast. It's tricky to code correctly. And it is very easy to write a buggy version by mistake, and Goodrich and Thomasia did exactly that. So if you have the textbook, at least the first 5 editions, I don't know about the 6th edition because I haven't seen it yet, but in the first 5 editions, their quicksort code on arrays takes n squared time if all the keys are equal. We're going to try to do better than that today. Our input to our array today will be, our input to our code today, our quicksort code, will be an array that I call A. And because quicksort is recursive, and I want to do recursion on this array, I have to be careful about that. I want to write my quicksort in such a way that I can tell it to just sort part of the array and not sort the whole array. So I'm going to give you 2 indices, low and high, and I only want quicksort to sort the items that are between A low and A high. And this allows me to have quicksort recursively call itself to sort just part of the array. At the top level, we want to sort the whole array, but we'll be recursively sorting parts of it on the way down. So our algorithm works like this. First of all, we choose our pivot v randomly. And then I want to partition the array into two pieces, I1 and I2. Keys less than the pivot, keys greater than the pivot. It turns out to be easiest and fastest to do that if I get the pivot out of the way. So I do that by moving it to the end of the array. In particular, I swap it with the last item in the array. So again, I'm just moving the pivot to the end of the array, or the sub-array, so that all the other keys that I want to partition are contiguous, and I can partition them really fast. Next thing I'm going to do is I'm going to employ two array indices called I and j. I am going to have I initially set to low -1, where low is the first key I want to sort. I'm going to have j initially set to high, the array index that now contains the pivot. And the idea is that as I go through, I and j will sandwich, so to speak, the items to be sorted or to be partitioned, not including the pivot. I'll show you what I mean by that in a minute, but basically all the keys we want to sort are between index I and j, not including index I or index j. And we will move I and j inward toward each other while satisfying the following invariants. We insist that all items at or to the left of index I have a key that's less than or equal to the pivot's key. And we will insist that all items at or to the right of index j have a key that's greater than or equal to the pivot's key. So let me demonstrate this now. Actually, let me draw that higher. Suppose that the array that I want to sort looks like this. Three, 8, 0, 9, 5, 7, 4, and the index low is the index of this array element here, the 3. The index high is the index of this array element here, the 4. I randomly select a pivot. Let's suppose I select the 5. So 5 will be my pivot. Now I want to partition this array. I want to have all the keys that are less than or equal to 5 before all the keys that are greater than or equal to 5. So the very first thing I'm going to do, as I said, is I'm going to swap the pivot with the last item in the array. So the 4 and the 5, I swap them. Everything else is in the same place as before. Now I set a pointer I that points to low -1, meaning it actually points to the spot in memory before the first item I want to partition, and j will point to the pivot. And when I have I there and j there, what that means is that I am working now on partitioning everything between those two. Not in counting I, not counting j. I'm partitioning these things in the middle. And now I'm going to take I and j and move them in toward each other while enforcing these invariants. And so the idea here is I will advance I forward until I reach a key that's greater than or equal to the pivot. So again, here's my array, 3, 8, 0, 9, 4, 7, 5. I advance I forward to the 3. That's less than the pivot. So I keep advancing I. I reach the 8. 8 is greater than the pivot 5. So I stops there. Then I will do the mirror image thing with j. I will decrement j until I find a key that's less than or equal to the pivot. So I move j back one step to 7. 7 is greater than the pivot. I move back another step to 4. 4 is less than the pivot, so j stops here. So I has now reached a key that's greater than the pivot. J has now reached a key that's less than the pivot, so I swap them. So I swapped the 8 and the 4, and that helps partition them. I want all the keys less than the pivot on the left, all the ones greater than the pivot on the right. Now I'm going to keep going. I'm going to keep advancing I forward until I find another key that is greater than the pivot. I'm going to keep moving j backward until I find another key that's less than or equal to the pivot. And this time something interesting has happened. I and j have actually crossed over. They've passed each other. When I and j meet in the middle, that means that we don't have to do any more swapping. So we're going to repeat this loop until I is greater than or equal to j, and then we stop. And when we have reached that point, now we will swap the pivot back to the middle. Specifically, we swap it with I. So I'm going to take the pivot. Remember, the pivot is this 5 over here on the far right. I'm going to swap it with I, and that gets the pivot back between the keys that are less than the pivot and the keys that are greater than the pivot. And I accomplish that by swapping the 5 with the 9. And now I have an unsorted array I1 that is keys less than or equal to the pivot. I will sort that recursively. I have an unsorted array I2 that is keys greater than or equal to the pivot. I will sort that recursively. So I want you to observe what the pseudocode that does this looks like. And I've got that further on. I have the wrong one there. 1 second. this work? So this is the pseudocode for Quicksort. It'll be in the lecture notes. I recommend that you study it carefully later on. The main thing I want to point out right now is the lines of code that do the partitioning. You'll see that there are these do loops with smaller do loops in the middle. I probably can't write on this, so this is not the right program to use. No. Let me try something different. All right, this is better. So the step that does the partitioning, this does almost all of the work, is that do loop there. So this loop does what I just said. It advances the pointer I forward repeatedly. It advances the pointer J backward until it finds items that you can swap. So you have an item that's too big on the left, you have an item that's too small on the right, you swap them, and here's the swapping step here. And then you keep going until the I and J pointers cross each other in the middle. And the really important thing to note about this is those inner loops are very, very small. So look at this do loop here. All it does is it advances the pointer I with the statement I++, and then it does one comparison. It compares that key to the pivot, and then it does that over and over and over again. So this is a very small, simple inner loop, and that means the compiler can make it run very, very fast, especially if you have a good optimizing C compiler. And likewise, the loop that goes backwards and does J is almost as simple and runs very, very fast. The reason why Quicksort has a smaller big O, or a smaller constant hidden in the big O than other n-log-n sorting algorithms is because those inner loops are so small and simple, and they just run really, really, really fast, especially if you have a good optimizing compiler. And that really is the secret to why Quicksort is considered to be the fastest of the n-log-n algorithms and is used a lot in practice. So again, when you're reading the lecture notes afterwards, study the pseudocode and make sure you understand how the whole thing works, but especially focus on those boxes. That's the reason why this is so fast. It's just because of the simplicity of the inner loop beats the simplicity of the inner loops of merge sort or heap sort, which have much more complicated inner loops. So one thing I want to especially focus on as well is how do you handle items that have the same key as the pivot? It's really tricky to handle these right, and as I said, Goodrich and Tomassia have gotten it wrong in all 5 editions of their textbook. So, I mean, what are they doing wrong? Well, when they have 2 keys that are equal, they don't split it. So they don't manage to subdivide them evenly into 2 equally sized sets. So if you have a bunch of 5s, what Goodrich and Tomassia would do is they would have, remember the I starts here, the J starts here. You start moving the I forward and the J backward. The way Goodrich and Thomasia would do it is the I goes all the way over here, stops there, and now you're done. You put all of the 5s into the left-hand partition. And with a pivot on the right, and you can see we're on our way now to n-squared land. We don't want to go there. So what can you do instead? Well, how can you be smarter about this? What we do in the version of quicksort I just gave you is that when I is marching forward, or J is marching backward, and you hit a key that is equal to the pivot, then you stop. So, I will take 1 step forward and hit a 5. 5 is equal to the pivot, so we stop. J will take 1 step backward. It'll hit a 5. 5 is equal to the pivot, so we swap. So we stop, and then we swap I and J. So I and J get swapped. We swap this 5 with this 5. That may seem insane, like we're wasting time swapping a 5 with a 5, but it's actually not. Because then what we're going to do is we will move the I 1 more step forward. We will move the J 1 more step backward. We'll swap again. We swap the 5 with a 5. We move the I forward and the J backward. We swap again, the 5 with a 5. We move the I forward. We discover that we are done. And now you'll notice that the I and the J are in the middle. So we're going to get a recursion where we quicksort these 3 5s, another recursion where we quicksort these 3 5s, and the pivot goes in the middle. And hey, we have a perfectly balanced split because we were smarter about the rules for what we do when we hit a key that's equal to the pivot. And now we're going to get an n log n sort instead of an n squared sort because we're getting these perfectly balanced partitions when all the keys are equal. Any questions about that? All right, go forth and sort. I'll see you on Monday. Oh, Friday my office hour is canceled. I need to let you know that the EECS department is having its faculty retreat out of town Thursday, Friday, so I apologize, but I can't be here on Friday.